Now you probably need to prepare yourself, putting multiple reactions in sequence to accomplish synthetic goal. What does it mean is, you want to make this from that, then what do you need to do? So that's something that you need to figure out. I mean, you see the difference between these two molecules. You see the amine on this side, it doesn't have that. So some of you may think that I'll just use ammonia as a nucleophile, and then this ammonia will kick this carbon, and then it make the hydrogen leave, then we get an SN2 product. So I'm asking you, is this a good way to make these products from that? And I'm saying this is not, because ammonia is a nucleophile, but it doesn't attack this carbon because there's these carbons are not in the division. There's nothing to leave. And then making hydrogen leave the electron, that's a hydride, which is a really, really strong base, and that's a bad leaving group. So this doesn't leave either. So you cannot do this way. So then how can you make this thing happen? So this cannot be done by one step. There's no way you can just do one step and get things done. You need to do a series of the reactions, and then that's something that you need to figure out. So let me first tell you, in order to make this happen, I mean, we can use an ammonia. It's not the problem with ammonia. Ammonia can be used. The issue is that this carbon doesn't have a leaving group. That's the reason. So what if we put leaving groups there? So make the leaving groups there, like positive leaving groups, halogens leaving groups, that make this carbon division, so ammonia will attack them. So how do you make the carbon positively charged, slightly positively charged? That's the when you put the halogen there, like a if you put the bromine on that carbon, now this carbon is electron deficient, and then you also have a bromine as a leaving group. So nucleophile like ammonia come and make an attack, and then bromine leave, and then you can make that. That's an SN2 reaction. So you can get it done. So we figured out one part of this problem. But another part of the problem is we still need to make this from that. So how do you make this from that? And then you notice that this is a bromination reaction. You put the bromine on the benzylic position. So that is a free radical carbonation reaction with this alcohol in chapter 4. You need the bromine, source of the bromine. So it can be bromine molecule or the MBS with a light. So what happened was you got the bromine radical forms that absorb the hydrogen, that makes a benzylic radical. That take up the bromine, I mean, from the produced by the MBS, and then the bromine is going to attach there. So you're going to get this product. This is the first step, and the second step is you treat that with a nucleophile ammonia, then you get the substitution done. So altogether, this cannot be done in one step. It needs to be done 2 steps. So when things need to be done sequentially, you have to provide a number. Which step is the first, which step is the second. So first step is an NBS with a light that makes this. Second step, you treat an ammonia to that and you make a product. So this is something called the multi-step synthesis. You need to use a multi-step of the reactions to make something. And then you got to think about what you need to have as intermediates. So this is kind of a strategic analysis. You have to make it. What do I need to make this? And then do I know any reaction to make that? You know, if nothing comes up, then you got to treat and find another way of looking at the problems. So this is something that you really have to get used to seeing it. And then it's possible from this test. So this is a multi-synthesis test. Questions are something that you would expect for the test too. So let me give another example for practicing that. How do you make this from that? I mean, clearly, it's not simple like the previous one. You have a double bond produce that carbon, and then hydroxyl groups now placed on that one. So we have to do the multiple things. sometimes it's not that easy to find out the forward. I mean, you have to start, let's say, you gotta go to, I don't know. This is October, so I always wanted to go Oktoberfest in, Bavaria. So you gotta go to Munich. Then what is the flight you want to take it from DFW, right? If you want to think about that, then you can find out the flight leaving from DFW. If there's no direct flight, you're gonna find out the stop that you can change the plane. You can analyze it for the forward, but sometimes you can walk backward. You have to find out what plane arrived in the München, and then you walk backward. Basically, that's something called the retrosynthetic analysis. You can analyze forward or you can analyze backwards. Probably you want to do both. And then you want to see those two analyses leading the same point, then we can probably cover all of them. Starting from this, going there, maybe a little bit too many things to think about because you got to make a double bond, you got to introduce that, too many things in mind, so it may not be easy to see that way. So I'd rather like to see things backward. Let's say we got to make this. So what would be something that we would need to make that? So what immediate, intermediate, right before the products, maybe this. If you have an alkyl halide bromine at that positions, then you can use a sodium hydroxide as a nucleophile, and then hydroxide attack this carbon, bromine lead, SN2 reaction will produce that, right? So that is a very good intermediate you can think of. I mean, this may not be the only intermediate, but I would say this could be something that you can think of. Now the question is, how are we going to make this from that, right? So kind of I have to step backward each time. So it's alpha bromide. You can make a bromination reactions. So if you have this propane, right, 3 carbons with a 1 double bonds, then you can do the allylic bromination with an NBS with the light. So you can see that I'm kind of walking backward and trying to go back to the starting point. I didn't get there yet, but at least I got somewhere. I kind of at the same carbon. Now I only need to make a double bonds. I only have to make a double bonds. So how to make a double bonds there? Double bonds can be made from alkyl halide by the elimination reaction, right? That's what we're talking about. So if you have a bromination done with this molecule, now going forward, you're gonna preferentially having a bromine on the 2 position because there's a more substituted positions. So most likely you're gonna get the bromine at the 2 position. Now we need to make this from that, and that requires just the base, probably multi-base, because we want to make sure that SN2 reactions are not happening. So to keep it topside, take this proton, making a double bond, halide kicks out. That is nothing but E2 elimination reactions. So now you make a double bonds there. What reaction number 1? You make a bromination reaction. Reaction number 2, you do the elimination reactions. The reaction number 3, you do the bromination again, but this one's an allylic bromination, right? So that position, allylic position, get brominated. And then step number 4, you treat the nucleophile hydroxide, replacing the bromine, that you get the product. The total number of the step is a 4-step process. But individually, you have to figure out. If you happen to use a different intermediate, that will change the synthesis. But to answer this question, there may be multiple right answers depending on what you choose to use. There may be multiple right answers. Maybe few answers, maybe some are right, not completely wrong. Then we try to come up with some partial credit. So I really want to try as much as you can. I mean, I know sometimes you may not be able to figure everything out, but I usually try something. If there's a step that makes sense, then at least we can solve with some partial credit. But we cannot do anything with a hopeless answer, unfortunately. If you get everything wrong, then No matter how long you write about it, I just cannot do anything. So,
Yes. Okay, right, probably like from that for me.
yeah, in this case, it's okay with the topic.
But I did like say, yes. I don't really would be right and probably that. Like, great.
Doesn't really work. NPS makes the program. That's what NPS does. NPS generate the bromines in solutions. That's it. We can use a bromine BL2 in some NPS if you want to. It's the same thing. It's up to you. I mean, that is something that I will do, but if you kind of a list display arrow, and each one clearly showing the reagents, then that should be fine. But you better start having this habit of the numbering them, just in case, then that they will come. Water, if using of water instead of that, it's not making SN2. Water is not a unique profile. You're better off doing SN1. But in this case, if you're doing SN1, because it's a linear system, and then there's nothing else you can do, I mean, this will even correspond with that. So you will probably get same thing, just it's a lot slower. So you will get a good amount of particle credit, I would say. And that's just a one step, not being more efficient. So you get the majority of the particle credit, just really lost. So we're going to look into that, how reasonable your choice of the steps. And if it's not optimum, not great, then we'll take some points away from the, as long as the others are fine. So that's why we're really going to look into what you write. So that's why you really want to write the steps. You want to show us this step you made that. That's how you use for the next step. That's used for the next step. If you leave the trace of the thought, we can see it, and we can probably acknowledge some of them if it makes sense. But if you just put only the answers, no traces, then nothing we can do. I don't know if some people don't, does that, even though there's huge space to write something about it. So don't just put your answers, you put your work up. And then we can see it. If it's there, then we can take a look. If it makes sense, we'll try to solve some points. It may not be everything, but at least some. So choose to write something on it, rather than just only an answer.
We also like the cations, okay, we were using the T50 oxide doing something. So
It's up to you. Sometimes you can use it, sometimes you can not put it there because that's not the most relevant. All right, so this is now you can see that there's a lot more steps involved. And the next one is a bit more complicated, even more difficult than the previous one. All right, so you want to make this from that. So we see some patterns. I mean, right now we can only use 5 different reactions, right? Halogenation reactions, SN2, SN1, E1, E2. So your choice of the reactions are 1 of 5. I mean, unfortunately, we didn't talk about so many reactions, so your choice is limited. So we cannot make this question too complicated because it's a choice of 5 and it's just different, way to put them together. But this question gets really complicated at the final exam after we use about 50 reactions. So then your choice is going to be a lot more. So that's why this type of question, we kind of give you a little bit of flavor, but it's going to get really difficult later. So you better get used to it. Anyway, you've probably seen the similar things. You got the allelic position again, so you already imagine, how that part can be created. And then, but these parts are new, right? So you're gonna think about, different way. So let's talk about one by one. Starting from the propane, so we need to make several things. I would easily say that in the product, clearly, you're gonna make a sulfur carbon bond. That bond has to be made. So sulfur is the heavy atom that you can probably make as a nickel bond. So I would probably imagine these can be produced by thiolate as an anion. That would be very, very unique profile if you have it. And then they don't need an alkyl halide. So if you have a bromine at that positions, and then you're using this thiolate, that would be the yielding SN2 reactions, and then you can make the product. So that now we break this the product into two pieces. Now we need to think about how each pieces can be created. This has to be created, that has to be created, but the previous example already given an idea that how that can be made, because that's alkyl bromide. So starting from that, same thing, bromination reactions will make a two-position brominated, and then you treat that with a strong base like a T-butoxide. Oh, I decided to go with that one first. Like a sulfur hydride, that's that one. It makes an attack, and then bromide kicked out. That's nothing but a SN2 reaction. It's available as a sodium salt. It's available as a potassium salt. Doesn't matter. You can use whatever. That's why you put the countercation because there's so many converters available. Anyway, this makes an attack. Kick this out. Nothing but SN2 reactions. So you can make this. But this is a neutral molecule that is a conjugate base of that. So how do you prepare this from that? You have to take a photon away from the sulfur, right? So if you remember how to make an alkoxide, that's the same thing. You're using like a sodium hydride, sodium metal, sodium amide. That strong base will come take this hydrogen, then you're gonna get this thiolate conjugate base. So that is a step that you need to make the nucleophile. The other side, you get the EP elimination reaction with the T-butoxide. The choice is made to the T-butoxide, not the methoxide, because there's a secondary alkyl halide. If you're using a small base, that may act as a nucleophile. You may get SN2 reaction done. So SN2 is competing with E2, and there's a secondary alkyl halide. So if you're using a bulky base and you shut down the SN2, you're only going to get the E2 elimination reactions. And then you need to brominate these positions. So that base can just an NPS and this. So each one, I know it's the arrows out, but underneath of that makes it really complicated. But if you write it together, you're starting with this. First reaction, treat an NPS. Second, you do the SN2 reaction with this. And the third, you take the photons away, you make this, put it there. Second step is the same molecule starting from MBS bromination, E2 elimination reactions, and then the bromination at limit condition, you make that. If you put that together, then you can make a product. So this requires a lot more steps. And then this type of question needs to analyze the product, how you're going to form that, what intermediate you need to create. And then, to make that happen, what reactor you will use, what would be the proper reagents. So this is actually the question that requires a lot of things, a lot of thoughts together. So this is why now it's not that difficult because only 5 reactors can use for that. But later on, this question is going to be very challenging. So I want you to be aware of this format of this question and what to do with it. Any question on this? All right. Continuing, and this is not that hard, but this one's not hard, but I just want you to think about this issue here. You have everything same, right? Except OH is replaced by the NH2. So how would you do it? Some of you probably say, how can use ammonia and kick a hydroxide out by SN2 reactions? And then this is a reaction that we keep saying that don't do it because not because the ammonia is not a nucleophile, but because the hydroxide is a bad living. That's a bad living, so it doesn't leave. So then how would you accomplish this? There are a couple of ways to do it. One, you have to change the hydroxy group to something else that can be a good living groups, like bromide. So if you're using it HBr, so hydroxy groups will be protonated, and then this will pop out as a neutral water. Then you get this cation, and then you're expecting this amine will capture that and make this out. It sounds like an absolutely good plan, right? You are taking the hydroxyl groups out as a water, you leave a carbocation, and then the nucleophile come and captures it. It sounds fantastic. Strategy seems to be fine, nothing wrong. But if you do this, I'm going to take some points away. So what's wrong with that? So what is the problem here is you just form a carbocation there, right? And then that you're just expecting ammonia sitting right next to it, waiting for the carbocation form and captures it. So that means you add HBr and then ammonia, put it together. You add a base and acid together. What would happen? They just capture the base, and then it just becomes a salt. It's just neutralized. There's no acid, there's no base. That's the problem. You cannot mix those two together. That's the problem. Then what other ways possible? And then once ammonia get protonated, this one doesn't have a lone pair. And the lone pair is the reason why it becomes nucleophile, why it becomes basic. But when that captures the proton, you can see that there's no lone pair. That ammonium groups is not basic, it's not nucleophilic, it doesn't do anything. Then what do you do? So that is the reason why we discuss tosylate. Tosylate is a sulfonyl groups. The sulfonyl chloride, tosyl chloride, used an alcohol, replacing the chlorine with the oxygen. You're actually going to get the tosylate ester, which is this ester, sulfonate ester. And then now this oxygen is a part of the living group. Oxygen can come off as a living group. So the nucleophile, I guess it's an ammonia here, attack that carbon and kick the sulfonate out. That's just nothing but SN2 reactions. So it's a two-step reactions, but you really have to recognize what you need to use. So that's the, tosylate becomes useful. It can make an OH as a good living group. You can do SN2 reactions. It also equilibration is possible with them too, because it's just a good living group. So tosylate is just, you can treat it as like a halide, but it's okay. So yeah, good question. I'll talk about that in the next step. So you can see that it still is a multi-step reaction. First step, you make a tosylate ester. Second step, that makes an attack, kick this one out as in two reactions. So it's a multi-step reaction. It's not something too complicated. Even though it's a simple one like this, still needs to be done. There's a couple of reactions in sequence. And then you think about what needs to be done first and what needs to be done later. So you have to analyze these type of things. Okay, going back to your question here. So that's the answer I just gave you. But what if you decide not to do that? What if you decide, I'm just going to treat an HBr and then let it make a bromide and then do the reaction like this? Well, I would say that you get the partial credit, but it's not that simple. You get this at the end. So this is something that I want you to think about carefully. It does go say the protonation done by H proton, right? This, and then this lead, that part is exactly the same as what we discussed. Problem is, this is a resonance stabilizer. So you get the resonance structures. Bromine can come capture this one, but bromine also can come capture that one. But between these two, which ones are more stable? This is a next to double bond, so we call it allylic. But allylic and primary, this is allylic and tertiary. So this is a more contributing than the other one. So we got the majority this way, this is the minor. So if this reaction go, then the bromide will capture that one. You're gonna get this as a major. Then there's another thing. You're gonna treat the ammonia to this, but this is a tertiary halide. SN2 reaction never goes on tertiary halide. Even though ammonia is a good nucleophile, it doesn't make an attack. So nothing happens until it falls out, makes a carbocation. Once it makes a carbocation, then it basically going back to this allylic system again. But this is still major. That is captured by the ammonia, and then you get that form as a major. But you get this one, that one form as a minor. That's why if you answer that way, you get a partial credit because you get the form from these irrational structures, but that's a minor compared to the other one. It's all about the stability of the carbocation. Allylic and tertiary carbocations are more stable than allylic and primary carbocation. So this is a major species that's just minus, and these are major contributors. Here are some minor contributors. The more reaction is going to happen with this form than the other form.